So it's 1 o'clock. Good afternoon, and welcome to today's coffee lecture offered by the Information Center Chemistry, Biology and Pharmacy from the ETH Zurich. My name is Emmanuel Meyer, and I will present you today the ACD Percepta software. ACD Percepta is a software developed by ACD Labs, which is a Toronto-based company founded in 1994. It's a very useful tool to predict physico-chemical and ADME properties from molecular structure. And these predictions are done based on empirical models, so QSAR models, mostly using advanced algorithm and training libraries. So these are the databases which are included, and there are more, so log-P, pKa solubility, and others. And these databases are used to train and to calculate, to predict these phys-chem properties like log-P, log-D, and we will have an example later on, pKa, that's very important, boiling point, and solubility. And there are also ADME properties. So absorption, that's the A of ADME, passive absorption, BBB permeation, blood-brain barrier permeation, distribution, that's a D. Then metabolism, cytochrome, P450, either the inhibition or to see if the molecule is a substrate and where it gets oxidized. This can be predicted. Also PGP specificity, which is important to predict the blood-brain barrier potential. And finally, oral bioavailability and also prediction on the daily dose, predicted dose. And then there are some additional tools like the profiler, ADME profiler, PK Explorer, structure designer, and we will have a short example. So all these modules are available at ETH Zurich. And if you're interested to test your molecules, just contact us. So it's not an open license for everybody, but you need to contact us. And drawing is done via the ChemSketch. This is kind of a ChemDraw offered by ACD Labs. So this is how the software looks like. You on the left side, you can start a new project in the data source panel. So it sources the open projects, the libraries which are used, the databases. In the middle, you have the workspace, which gives you all the accessible modules like log-P, log-D, and so on. This long list of possibilities to calculate. And on the right side, you see the molecule when it's there, and also the results of the calculation. So, for example, if we look at the log-P prediction, it relies on a database, and if you open the database, it has more than 18,000 entries. That's a huge database. And if you want to see what is actually log-P, then you can click on the question mark at the top, and there's a large documentation on the software, but also on the parameters. And you can learn a lot on the parameters and also the underlying scientific articles. So we gonna start with a little case study, a medicinal chemistry case study using one example, nortriptyline, which is a tricyclic antidepressant, a very old drug since the 60s on the market. And if you want to start a project, so you click on new project on the left, and then you either import the molecule, and I'm gonna show you this with a pointer. So you import the molecule from a file or from a Smiles code or Inchi code, or you draw it, or in this case, just type the name or part of the name, and it's already in the database. So I typed nortriptyline, and the molecules pop up. And then you can start to calculate. So you switch the module, you go to log-P, and you have different kind of algorithm. The first one, the classic, looks at increments of the molecules. So part of the molecules which have a known log-P, calculated log-P, and log-P, as a reminder, is the partition coefficient between an organic phase and water, octanol-water. And that's a formula. And the program calculates the log P being 5.65. Never take any value for granted, any predicted value for granted. You look at the reference, see, does it make sense? And then you can also look at the other algorithm, which looks at similar compounds. So not increments, but similarities between compounds. And there, the log P is lower with 4.4. And because there is no consensus, the program gives you a consensus here, and you can look it up. But remember, log P calculation assume that the compound is in its unionized form. And here we clearly have a basic center. That's why the first question would be, what is the pKa of this basic center? Typical exam question. And here, so you change the module, you go to the pKa module, and here, again, it looks at fragments. And there is a fragment which is similar to this one, and the pKa is 10. And then there is the Gallas algorithm, which looks at similar compounds. And here it's practically the same value, 9.9. And what's really cool is to see underneath, there is a graph where you can click and drag the slider here to see the calculated fractions of the individual neutral and protonated form. Yeah. So this is what you learn very early on in your courses. And at a pH of 9.9, you have 1-to-1 ratio of both form neutral and protonated form. So that's the definition of a pKa. And of course, if you have more than one form, like this lisinoprylanase inhibitor with 2 acidic groups and 2 amines, this gets a bit complicated. It's really interesting then to see what are the distribution of this charged species across a range of pH. But remember, so we have a pKa, a basic center, and if you have a basic center, you should use the log D, and the formula is given here, which accounts for the pH and the pKa. And for example, this log D, which is a measure of lipophilicity, will change according to the pH of the environment. For example, stomach has a pH of 1.7, goes to 8 in the column. So you would like to know what is the log D at different pH, and in this graph, you can look how this curve evolves over the pH. And in the jejunum at a pH of 6.5, the log D is at 2.69. And this is a good range for permeable compounds, or for compound to be permeable. But is the compound permeable in humans? So you can predict the passive absorption in the intestine, and it's predicted to be 100% via the transcellular route. So there are 2 basic routes, transcellular, paracellular. In this case, because it's a larger molecule, it's transcellular. And this is in agreement with the reference compound, the reference value. And you can also look at the CACO2, which is another method, and this is an experimental cell-based method to calculate permeation. It's a colon carcinoma cell, widely used to calculate the permeation, and you can also predict the values there. So it's absorbed. Now we have to know it's at one point it needs to go into the brain. And in the brain, there is an important receptor called the PGP receptor, which takes place in the efflux, pumps out any drugs or many drugs out of the CNS compartment. And in this case, nortriptyline is predicted to have a low probability to be efflux or pumped out of the CNS compartment, low to none. And the reference value is given here. So it's not a PGP substrate, which is a good result if you want to go into the brain. Okay, but before it reaches the brain, it needs to enter the systemic station, and this is given by the oral bioavailability. It's a parameter which calculates what is the fraction which comes into the circulation after having been absorbed and metabolized by the liver. And here we see a 99% oral bioavailability, which is perfect. And what's interesting with the software that you can change the dose. And if you increase the dose at one point, your molecule will not be soluble anymore. And this will then affect the bioavailability. In this case, we have a very good solubility due to the basic center, and this can also be calculated or predicted by the software in one of these modules. So now the compound is in the circulation. It needs to reach the brain, and the brain has a special barrier called the blood-brain barrier. And this can be also predicted. And here, ACD Labs uses two parameters, log BB and log PS. And here you just have to look at the documentation. There are papers describing in details what this means. If you plot these two parameters, log BB versus log PS, which includes the fraction unbound, this is part of the distribution, then you can classify compounds according whether they are active or inactive in the CNS. And fortunately for this drug, it's in the active part. So the green square here shows nortriptyline. It's CNS active, not so surprising because it's a marketed antidepressant and should reach the brain. So that's a journey through the ADME profile. There's one missing, important one, which is the T of ADME, the toxicity. You can also predict the cytochrome P450 inhibition. And so you have usually 4 or 5 major isoforms, and they are listed here. And not too surprisingly, the 2D6 isoform of cytochrome gets flagged. Yeah, minor inhibition, and that's because of this basic amine and the aromatic part. So this is possibly cytochrome P450 should be then measured in the lab. Could be also substrate, and then you have here another tool to predict if it's a substrate of P450. And overall, then you can look at the overall profile with the ADMET profiler and see how with color coding, red to green, PhysChem, ADME profiling drug safety. We looked at the CYP profile, and overall, it's a pretty nice profile for a drug. And now, if you would like to have your own IDs and own drugs, you can import a whole list of molecules, calculate the properties. It gives you a table. And let's go back. And then you can do also with this imported structure, you can make changes to the structure. So either with your own molecule or starting with this nortriptyline and see how the parameters evolve. So that's a very useful tool to before testing or yeah, to see how the molecule could behave in vivo and in vitro. So with that, yes, I'm at the end. Thank you for your attention. I would like to highlight the next coffee lecture, which takes place tomorrow by on Manchester academic phrase by Yoshi Sadolens. And then there's the next one on Thursday by Gina Canarozzi. Thanks a lot for your attention.